Hello again, Math 20-1s. In today's lesson, we're going to talk about geometric series, and you can find this lesson on page 63 of your Math 20-1 workbooklet. Just a quick little reminder, just to clarify the difference between a sequence and a series. So a sequence is a list of terms separated by commas. In this particular sequence, it's a geometric one because you have 2, 4, 8, 16. You'd have a common ratio of 2. A series is when you take all the terms in a sequence and you add them together. So we can immediately identify that by switching all those commas to plus signs because we're going to find the sum of all the different terms within the sequence. And again, that's referred to as a series. We want to get an equation for the sum of a geometric series, and we'll do a very, very quick derivation here. So in a nutshell, this is kind of how it works. If I wanted the sum of a series, Sn would be equal to, you could take term 1, you could add term 2, you could add term 3, add term 4, add term 5, and so on until you get to the last term in the actual sequence. Now, if we start to actually replace the terms here with correct variables, so we can do this in terms of just thinking about it logically and using a general term formula. So T1 here would be A. T2 you can calculate by taking A and multiplying by the common ratio. T3 you can get by taking term 2 and multiply by the common ratio. So AR multiplied by R would be AR squared. Term 4 you can get by taking term 3, which is AR squared, multiplied by the common ratio, which would be AR cubed. To get the value of Tn, you can just use the general term formula for a geometric sequence, which is T of n is equal to A R to the power of n minus 1. So I've got this top equation here that shows me how I could calculate the sum of a geometric series. I'm just going to box this equation right now, and I'm going to call it equation number 1. Now, what I'm going to do, or I'm not going to say what I'm going to do, what the book does right here is they show a second equation on the line directly beneath it, and it's not totally clear where exactly this line comes from. So we're going to call this one equation 2. So I'll just box this whole thing and call it equation 2. Then I'll talk about where it comes from. To go from equation 1 to equation 2, equation 2 would be equal to equation 1. And what we're doing is we're taking every single term in equation 1 on both the left and right-hand side of the equation, and we're going to multiply every single term by an R value, the common ratio. So you can see this. If I take everything right here and I multiply it by R, then you'd have R times S of n. S of n just means the sum of the terms in the sequence. Then you'd have A times R is AR. AR times R is AR squared. AR squared times R is AR cubed. AR cubed times R would be AR to the power of 4. And then this one right here, I'm not going to even show this. So if you have like AR to the power of n minus 1, and you were to multiply that by R, this R would have an exponent of 1. So to combine these common bases, you can just add the exponents. And if you add the exponents together, it would be n minus 1 plus 1. These two 1s would cancel off, and you'd just be left with AR to the power of n. Now, what I want to do is I want to take equation 2, and I want to subtract equation 1. So I'm going to go equation 2. And I'm going to subtract equation number 1. Okay, so we're going to go, usually you put the equation that you're like, you put equation 2 on the top and equation 1 on the bottom, and I subtract them, but I really don't want to rewrite out all the terms in these different sequences. So here's how things would cancel off here. On the left-hand side, you would have RSN minus SN, okay? So you have RSN minus SN, no problem. Okay, now on the right-hand side, a bunch of terms start to cancel, okay? Now the A term doesn't cancel right here, but what does cancel is AR squared, AR cubed, AR to the 4 would actually cancel. This AR to the n minus 2, which I didn't show it in the second series, but that's okay. AR to the n minus 1 would cancel with AR to the n minus 1. So the only terms you're going to have left would be, you would have, I'll just circle all of them. So you're going to have this one, you're going to have this one right here, you're going to have this one, and you're going to have that one. Because you're going equation 2 minus equation 1, you would then have R S of n minus S of n would be equal to A R of n subtract A. And what you can then do here is on this left-hand side, you have there's a common factor. You can pull out the S of n. And if you pull out the S of n, you would then have R minus 1 remaining. And then to get the equation for the sum of this geometric series, all you need to do is divide both sides of the equation by R minus 1. Divide by R minus 1. This would cancel. And then you'd be left with S of n is equal to A, R to the power of n minus 1 over R minus 1. R cannot be equal to 1. Otherwise, you'd end up getting 0 in the denominator. And furthermore, it doesn't have a growth factor then. It would just have a common ratio of 1. If you would rather write down A as T1, then you can also write it down like this on the right-hand side here. Both these equations are on the formula sheet. These two equations are good if you want to calculate the sum of a geometric series and you know the value of the first term, you know the common ratio, and you know the number of terms that are actually in the sequence. There could be a situation, though, where you do not know there could be a situation where you do not know the number of terms that are actually in the sequence, but you might know what the last term is, what T of n is. So I'll say a last term known. In which case, there's a couple of other formulas on the formula sheet. This is similar to the arithmetic series as well. There was also a formula where you could calculate the sum if you didn't know the number of terms in the series, but if you did know what the last term was. And the equations we have are S of n is equal to R T of n minus A over R minus 1. Or if you don't want to write down the A here, okay, you can just write down R T of n minus T1 over R minus 1. Now, this example just wants us to quickly show, well, how could you, for example, take this equation right here and then obtain this one? How can we show these two equations are actually equivalent? Okay, so I want to show that this S of n equation is equivalent to this one right here. Now, if you look at the two equations, the denominators of the two equations are identical. Okay, you have R minus 1, R minus 1. So really all I need to do is I just need to show that the two numerators are equal to each other. I need to show that R T of n minus A is equivalent to A R of n minus 1 in brackets. And we can do that quite easily. Okay, so here's how we do it. For a geometric sequence, I know that the general term formula is T of n is equal to A R to the power of n minus 1. What I'm going to do is I'm going to make a quick little substitution. So I'm going to take this equation and I'm going to replace T of n with A R to the power of n minus 1. If you do that, you then have S of n would be equal to r times, I'll do the substitution in a different color just so you can see it a bit more clearly. So you have a r to the power of n minus 1. And then we still have that subtraction a here. We don't need to put it in. Yeah, I guess we can put it in brackets if we want to. Okay, and we're going to subtract a and divide that by r minus 1. Now, I'm going to move the r into the brackets here. So if you do that, you would then have a times r to the n minus 1 over r minus 1. And then I just want to combine the exponents on the r terms. So this r has or the r variables, this r has an exponent of 1. And if you combine the exponents, you would then get, we got to put this minus a here. Okay, if we combine the exponents, it would be 1 plus n minus 1, which would actually just eliminate the 1 and the negative 1. So that would become a r to the power of n minus a, and then divide this by r minus 1. And then if you just factor out a common a out of the top, you get s of n is equal to a r to the power of n minus 1 over r minus 1. Therefore, this equation and this equation up here are equivalent. The top equation is good if you know what the first term, the common ratio, and the number of terms in the series are. The second equation is good if you know the common ratio, you know what the first term is, and you know what the last term in this series is, but you don't know how many terms there actually are. So let's look at various examples now where we can make use of these equations. So example 2, determine the sum of the first 15 terms in the sequence -5, 10, -20. All right, so we want to determine the sum of 15 terms. And if I look at the sequence here, your first term in the sequence is -5. The common ratio, well, how do you go from -5 to 10 if it's geometric? You'd multiply by -2. So -5 times -2 would be positive 10. You can double check that. 10 times -2 would also be -20. So your common ratio R would be equal to -2. And I want to calculate S of n. I'm going to use the first equation to do this one. So that equation looks like S of n. And I like to write down my term 1 as A, not T1. So you have S of n would be equal to A, and then R to the power of n minus 1. And then divide this all by r minus 1. So let's sub the numbers in. So this would be equal to a, which is -5, and then r, which is -2, to the power of n, which is 15, minus 1. And then divide this by -2 minus 1. Now, you can plug this all into your calculator in one shot. What I'd recommend doing, though, is I just put the entire numerator and denominator in brackets. Although if you did want to break this down a little bit more step by step, you could. But I'll just quickly show you how I would do it. So top in its own set of brackets, and then bottom in its own set of brackets. And then let's go ahead and plug this in. Okay, so the top would be, we would have -5. And then we have in brackets, we're going to open the bracket up here. So I'm just following basically the bracket placement that I have. Okay, so -5, and then I have -2, all to the power of 15. Okay, hit right to get out of the exponent, minus 1. Okay, close the bracket off. I need to put another bracket here. So you have 3 brackets that have like the curve that I suppose opens towards the, left. Okay, 3 of these brackets. So I need to have one more that points towards the right just to kind of close it off. Okay, so that's the numerator. And then divide by the denominator. So we'll use a bracket to put everything in the denominator in. The common ratio is -2. So I'll put that in brackets, -1, and then close that off. And then this is equal to negative 54,615. So if you did want to plug it in one shot, that is what it would need to look like. Okay. But if you find that a little bit too much to plug in your calculator with like the placement of the brackets, then I would just simply break it down step by step following the correct order of operations. Okay. So this is, we'll say it's S15. Oops. We're going to replace the n with 15. So S15 is negative 54,615. Example 3. So we have a series, and again, I can see that with like the plus and the negative signs. So what do we know in this situation? I know the first term, which is 4. The common ratio, well, how do you go from 4 to negative 12 to positive 36? You're going to multiply by negative 3. 4 times negative 3 would be negative 12. Negative 12 times negative 3 would be positive 36. So you'd have r is equal to negative 3. I don't know how many terms there are here, but I do know what the last term is. The last term, t of n, has a value of negative 8,748. And I want to calculate S of n. I don't know how many terms there are. That's okay, though. We're going to use the second equation to do this. So that equation looks like S of n is equal to r t of n minus a divided by r minus 1. Let's plug everything in here. So r is negative 3 times t of n, which is negative 8,748. Subtract 4, and then divide by negative 3 minus 1. And again, I'll put the top and the bottom in its own set of brackets. I don't mess the order of operations up. And I'll go back to my calculator and just quickly show the work for this. So this would be, here's one bracket to open up the entire numerator, another bracket to sub in the negative 3, the common ratio, and then multiply by another bracket to sub in the value of the last term in the series. And then we're going to subtract 4. Okay, close the bracket off. So this is going to close the numerator off. And again, you can see you have two of these brackets that open towards, I don't know if that's the correct wording, open towards the left. It looks like they're like firing towards the left. And then I have 3 of them. 1, 2, 3. So you should have like an equal number pointing in each direction is basically what I'm trying to say. Okay, divide by, open bracket for the denominator, bracket for the common ratio, which is negative 3, and then subtract 1, close the bracket off, and you get negative 6,560. So despite the fact I don't know how many terms are actually in this series, I can still calculate the sum. So negative 6,560, and we'll leave it at like that. Fourth example, the sum of a certain number of terms in the series. So again, we don't know how many terms there are. So we have negative 2 plus 8 plus negative 32 is negative 104,858. What is the last term in the series? Okay, so what I know right here is I know the value of the first term. That's a is equal to negative 2. I know the value of the common ratio. I can just look at it quickly. How do you get from negative 2 to positive 8? You multiply by negative 4. We can double check that again. How do you get from 8 to negative 32? Multiply by negative 4. 8 times negative 4 would be negative 32. So you have negative 4. Now, I know what this, it actually tells me what the sum is. Okay, so this number at the end right here is not the last term. It's the sum of the actual series. So that's S of n is equal to negative 104,858. And then what we want to do is we want to calculate the last term. The last term is t of n. Okay, this is going to require a bit of formula manipulation to do. So let's write down the equation that has the last term in it. So that's the one we used in example 3. So that's S of n is equal to r t of n minus a, and then divide by r minus 1. If I was manipulating this equation in physics, I would manipulate everything in terms of the variables first, but for a math course, I'm actually just going to plug in the numbers and just try to isolate the one variable. So S of n is negative 104,858. And this is equal to r, which is negative 4, times t of n, which is the unknown variable we're going to try to solve for, minus a. So subtract negative 2. So we're going to have to add a positive there in a moment. We'll clean this up in a second. Okay, divide by r, which is negative 4, subtract 1. So this would then be negative 104,858 would be equal to negative 4 t of n. And then subtracting a negative, we're going to add a positive. So it's going to be plus 2. And then I'm going to divide by negative 4 minus 1 would be negative 5. Now, in order to solve this, I need to get this negative 5 out of the denominator. The easiest way to do it is just to cross multiply because you have a single term on the left-hand side of the equation. Cross multiplying would be equivalent to just multiplying both sides of the equation by negative 5. Okay, so then this would be, if you multiply this, negative 104,858 times negative 5 would be 524,290. And this would be equal to negative 4 t of n plus 2. So now we just have a linear equation we need to solve. So to solve this, first of all, so you need to do the reverse order of operations. I'm going to deal with this addition term first. Let's subtract that. Minus 2 from both sides, minus 2 from both sides. That's going to give me, this is, yeah, okay. So that's going to give me 524,288 would be equal to negative 4 t of n. I think that's right anyways. Just want to double check this here. Yeah, if that's negative here, this bottom portion is also a negative. Negative times a negative is a positive. Okay, so, and then we're going to, now we need to just get rid of the negative 4 terms. So just divide both sides of the equation by negative 4. Divide negative 4. Divide negative 4. So 524 divided by negative 4 is going to be t of n is equal to negative 131,072. Okay, that's the last term in the sequence, or sorry, I should say in the series because we have the plus and the plus signs. Okay, fifth example. In a geometric sequence, the fifth term is 1,024 and the common ratio is 4. Find the sum of the first 7 terms in this sequence. All right, so I know when n is equal to 5, term 5 is 1,024. The common ratio is 4. And I want to find S7. The problem with this question is regardless of which sum equation you use, you need to know what the first term in the sequence is, or the first term in the series is. So we need to figure out this first. Now, we can get the first term in the sequence by using the general term formula. So the general term formula is t of n is equal to a r to the power of n minus 1. And we're going to solve for a using this information here. When n is 5, t of 5 is 1,024. So this would then be t of 5 would be equal to a, which we don't know, multiplied by the common ratio, which is a 4, to the power of 5 minus 1. And t of 5 is 1,024, which would then be a, and then we could have 4 to the power of 4. 4 to the power of 4 is 256. So we'd have 1,024 is equal to a multiplied by 256. To get a by itself, just divide both sides of the equation by the 256. So divide by 256, divide by 256. The 256 cancels, and I'm pretty sure it's going to give you an a value that is 4. All right, now that we know what a is, then we can calculate S7. I'm going to use the first series equation because you know what a is, you know what r is, and you know the number of terms we're going to calculate. So we're going to figure out S of 7. So that's the sum of the first 7 terms. All right, so we use the equation. S of n would be equal to a r to the power of n minus 1 over r minus 1. And we want to figure out S7. So S7 would be equal to a, which is 4, multiplied by r, which is also 4, to the power of 7 minus 1. And then we're going to divide by 4 minus 1. And I'll put the numerator and denominator in their own set of brackets, just so I can get the order of operations correct. And then we'll go to the calculator and determine this. So this would be, okay, open bracket for the numerator. Then I would have 4. And then open bracket for the r to the n minus 1 term. So we'd have 4 to the power of 7. And then we're going to subtract 1, close that bracket off, close it off again. Okay, so the numerator is dealt with, and then divide by the denominator, which would just be 4 minus 1, close the bracket off for the denominator, and then I get 21,844. All right, we're just going to do one more example for this lesson. I'll actually break it into 2 parts. Just I feel as though some of the previous ones have been a little bit too long. So I'd rather just kind of slow down a little bit and break this one into 2 different chunks. All right, determining the number of terms in a geometric series. So now n is going to be an unknown. All right, so the sum of n terms of the series, 5 plus 15 plus 45 is 16,400. Okay, so let's identify what we know here. I know that a is 5. I know the common ratio is, how do you go from 5 to 15, from 15 to 45? You multiply by 3. And I know the sum of the series. Again, this is the sum, not the last term in the series. And that's 16,400. And we want to figure out what n is. I'm going to start off by writing down the geometric series equation, the one that has a, r, s of n, and n in it. So that's the one that's s of n is equal to a, and then r to the power of n minus 1 over r minus 1. So we're going to sub in all the values now. So s of n is 16,400, and that would be equal to a, which is 5, multiply by 3 to the power of n minus 1 over 3 minus 1. Okay, the denominator would just simplify to 2. So 3 minus 1 would be 2. And then I want to get rid of the denominator. So I'm just going to again cross multiply. I'll bring this 2 up to the right-hand side, which I can do because bring it up to the left-hand side because the left-hand side just has a single term on it. So this would then give you 16,400 times 2 would be, I think it's 32,800. Let's double check that. Yeah. Okay, so you have 32,800 is equal to 5, 3 to the power of n minus 1. I also want to get rid of this 5 here. So I'm going to divide both sides of the equation by 5. Divide by 5, they cancel off. And then dividing that by 5 would give you, so 32800 divided by 5, they give you 6560. And then that would be equal to 3 to the power of n minus 1. And again, I want to get the term that has the n attached to it isolated. So now I'm just going to add 1 to both sides of the equation. And if I do that, I would then get plus 1, and then I would have 6561 is equal to 3 to the power of n. Now, once we get to this stage here, I'll just box this equation because we're going to have to solve this using 2 different methods. So I'll box it. To do this algebraically, once again, we require the use of logarithms. But we can actually attempt, it says like, try to use that common base trick. So the idea right here is I want to take 6561 and I want to write it so it has a common base of 3. Because if it has a common base of 3, then I can set the 2 exponents equal to each other. So the question is 3 to the power of what? Okay, leave it as a blank, would be equal to 3 to the power of n, and 3 to the power of what is 6561. So we can kind of go through, I suppose, in like a trial and error fashion to get it. That's a pretty big number, so maybe I'll start off with like 3 to the power of 8 and see what happens. Okay, that was a fluke. I don't know how I got that in one shot, but I mean, anyways, 3 to the power of 8 is 6561. Otherwise, I would just keep going 3 to the power of a bunch of different exponents until you see what it is. Okay, so that would be 3 to the power of 8 is equal to 3 to the power of n, and that's simply it. Then you can, if the bases are the same, you can set the 2 exponents equal to each other. Therefore, n would be equal to 8. We're done. Now, we can also use the graphing calculator to do this. Let's take this boxed red equation. So 6561 is equal to 3 to the power of n. In the place of y1, we're going to plug in 6561. That's going to be a horizontal line that has a y-intercept of 6561. So we're going to adjust the window settings so we can actually see that. Okay, y2 is going to be, we're going to put in 3 to the power of x, and then we're going to use that intersect feature. Okay, so let's go to the graphing calculator and do this. So let's clear our old equations. So y1, we're going to plug in 6561. y2, we're going to plug in 3 to the power of x. Let's go zoom standard. We're not going to be able to see anything probably, but okay, so I can see the red one, but I can't see the y1 equation because it's a horizontal line that passes through the y-axis at above 6,000. So let's adjust the window settings so I can see it. So let's go to y max and make it like 7,000. And now let's graph it and see if we can see the intersection point, and I can. Okay, the intersection point is up and towards the right here. So we'll go second, and then trace to get calculate. Pick intersect. Okay, bring that cursor over to the intersection point as close as you can. hit enter, bring this cursor up to the intersection point, hit enter, get it to guess the solution, and it tells me that x is 8, y is 6561. So x is 8, y is 6561, and x is n. So the number of terms would also be 8, which we already knew by using that common base trick in part A. All right, we're going to stop here. Example 7 is actually quite a difficult problem, so I wanted to just approach it from like the start of a new lesson, and again, give it more time to kind of get caught up on some of the work here. All right, so for now, you can do page 67, numbers 1, 2, 5, 6, and 10. And I'll talk to you in part 2 of this lesson next time.